Hi, and welcome to this showcase about solving complex problems with simulation and AI done in collaboration with our technological partner, Pathmind. I'm Luigi Manca, I'm from Italy, and I'm the Director of Simulation and Digital Twin Practice at the Industry's Excellence Division of Engineering Informatica Group. Before leaving the stage to my colleague Sahar from Pathmind, just let me spend a few words about the company I'm representing here today and about our North American branch, Engineering USA. So the engineering group was established in Italy more than 40 years ago and is one of the main players in the digital transformation industry for both public and private sector. The group designs, develops, and manages innovative solutions for business areas where digitalization generates major change, such as digital finance, smart agriculture, augmented city, digital industries, and so many others. The group can count on many assets spreading through proprietary solutions to data center and a worldwide presence, with more than 12,000 associates. Engineering USA is our organization's North American branch with an headquarters in Chicago and a team of 100 specialists focused on the technological transformation of the manufacturing and transportation sector. Also, it is worth mentioning that we have one of the few technological practice focused specifically on simulation and digital twin. And this is one of our fastest growing area within our global industry excellence division. So both in Europe and North America. At Engineering, we are partnership together with Pathmind because we strongly believe that this kind of approach brings many advantages to the industrial organization we work with. Today, my colleague Sahar is showing you a practical demonstration of how straightforward he is applying deep reinforcement learning techniques through the Pathmind platform and focusing on the deep reinforcement learning elements in any logic that then can create a bridge with the brain embedded in the Pathmind service. And she presenting this service as well. So I leave the stage to you, Sahar. Thanks for watching.
Thank you, Luigi, and hello to everyone. My name is Sahar. I'm a simulation engineer at Pathmind. Pathmind is software as service that enables users to use AI as their decision automation tool. You can use Pathmind to train AI agents in simulation environment. These AI agents will interact with the environment and learn to make decisions in a way that will optimize your objectives. Later, you can deploy these trained AI agents in your real-life business operations or use them as a decision support tool. In this presentation, we will briefly talk about advantages of reinforcement learning, the obstacles that are holding RL back, and how Pathmind can help you to overcome these obstacles so you can easily integrate and deploy AI in your operations. We will walk you through a task allocation problem and show you how to create an AI agent using Pathmind to optimize objectives. If you have any questions, please feel free to post them in Q&A chat window. We will gladly answer them in the session after the presentation. A big advantage of RL in the context of AI is that it can optimize conflicting objectives when there are multiple simultaneous decisions to be made in presence of high variability. For example, a manufacturing plant might need to optimize throughput while dealing with fluctuating energy price, so to keep costs under a certain amount. Reinforcement learning is able to handle these more complex scenarios and outperform other optimization methods. So what has held RL back up until now? One obstacle is that RL is highly compute intensive. Usually you will need to run multiple experiments in order to get a good result. On a normal computer, it might take days to train an experiment, and you can't run experiments in parallel either. Next obstacle is that AI agents need a realistic environment to be trained in. So you need to program this environment, verify that it reflects the reality, and validate it. Next is sensitivity to hyperparameter tuning. So hyperparameters such as train batch size, learning rate, neural network architecture, policy temperature, rollout workers, and episode lengths affect performance of reinforcement learning. So you need to carefully select these parameters. Last one is that you need expertise in deep learning and dynamic programming. To choose the best algorithm for your AI agent, you not only need to be familiar with many algorithms, such as DQN and PPO, you also need to know how to implement them. So Pathmind offers to solve all these problems. For compute intensivity, since Pathmind uses cloud, training experiments complete much faster, and you can start as many experiments as you want in parallel. Pathmind also interfaces with simulation softwares such as AnyLogic. AnyLogic comes with many built-in libraries that makes creating a realistic replica or a digital twin of your system much easier. It is also much easier to validate and verify these models. Pathmind also uses a technology that automates tuning hyperparameters. So while training, it finds the optimal combination of hyperparameters for your problem. Reinforcement learning scientists in Pathmind are experts in many algorithms, so they can choose the most suitable one for your problem. They also are always researching about these algorithms and further refining them for industrial use cases. Let's demonstrate end-to-end how Pathmind works by going through an example model. This is field service model. There is a fleet of equipment units that are distributed geographically within a certain area. These equipments could be vending machines, wind turbines, or anything else. Each piece of equipment has a remaining useful life that decreases based on a random rate. Remaining useful life affects how much revenue an equipment can produce. Repair cost is much higher than maintenance costs, so it is much better to attend to an equipment before it reaches the failed state. Since we do not know the actual remaining useful life, we can only make predictions about the state of an equipment. The original task allocation method used in this model was to send service crew to equipments when their estimated remaining useful life fell below a certain limit. Service crew would attend to equipments in a first-in, first-out manner. I will change the model to run with a heuristic logic now. As you see, failures are much frequent when using heuristic. Service crew prioritizes equipment that has requested service first. So they drive longer distances and ignore the nearby equipments that need service too. Pathmind policy is able to increase profit by about 65%. Here is how Pathmind policy is able to make decisions and optimize this system. The AI agent at each step uses observations to make decisions. Observations include all the information that is needed to make an optimal decision. For example, in this system, what the AI agent sees is the location of the service crew and the state of each equipment, like predicted remaining useful life and whether it has already failed or not. Based on the observations, the AI agent decides to assign an equipment to service crew or send the service crew back to home location. After doing the action, the AI agent gets a reward based on how this action has affected the objectives that we have given to it. For example, in this model, reward is calculated based on how much the policy is able to minimize failures and also minimize the driven distance, so hence maximize profit. You can integrate Pathmind in your own simulation models. You just need to add Pathmind helper as a library to any logic and add a Pathmind helper item to your simulation and define observations, metrics, and actions related to the problem you want to solve. And then export the model as a standalone jar. So let's do it. This model is ready for RL. Let's export it as a standalone jar. Next step is to go to Pathmind web app and start training. But to do that, you need to first sign up. There is a free account option, but there are also pro and enterprise options too, which give you unlimited access and include support options. But for now, you can just sign up for free. So you create your account. After that, you sign in. You will see a page much like this. What you do is first to create a new project, give a name to it, the model we are going to do is field service view 2, for example. Then upload your exported model. This step is optional. You can add the model ALP file as well, but we'll skip it for now. You can write a note for your model. Let's skip it for now. Here, you can choose the goals that you want to make for each metrics that has been defined back in your model. For example, in the field service model, we want to minimize crew travel cost, minimize the total number of failed equipments, maximize the profit, and let's say minimize total work cost. Here, as you see, there will be a reward function automatically created for you. So all is ready. You can start training this experiment with this reward function. You can create another new experiment, and this time, for example, let's say that we do not want to include travel cost and total work cost in the reward function. Let's see how this reward function will do. Let's start another experiment with that one. Let's start another one. So from the heuristic baseline, we know that total number of failed equipment is in order of 100, and total profit is in order of 1 million. So in order to make these two reward terms in the same magnitude or in the same scale, let's say we divide total number of failed equipments to 100 and divide total profit to 1 million. This is called reward normalization. So you basically make all the reward terms to be in the same magnitude. So they both are using the same currency now. They are in the same order, so they affect they drive the training in the same with the same magnitude. Okay, let's create another one. Let's say we care about profit about 2 times more than we care about total number of failed. So if a failure will end up maximizing the profit, let's that failure happen. Let's train that one. Let's next start a new experiment. Here, as you see, this is the list of the observations that you have defined in back in your model. So let's say I want to know if I exclude time from the observation, how that will affect my results. So let's deselect time and start another training. So as simple as that, you can start as many experiments as you want and let the experiments run until they finish, and you will receive a notification that experiments are done. So let's look at a finished experiment. For example, here I have some experiments that are finished. You see that this experiment has been able to increase total profit to about 1,695,000, and total number of failures is 8 equipments, give or take 6. So these values you see here are the uncertainties, and this value is the mean value that is calculated for each of these metrics over a number of simulation runs. So let's look at travel costs. See, first, the policy has reduced the travel cost a lot, thinking that reducing the cost will end up maximizing profit, but it has seen that that policy is not working, so it has decided to increase it. And this is with this diagram, you will see how a metric will evolve through iterations of learning. Let's look at number of failed equipments. See, it started from 90 and it goes down, and the policy is able to minimize it to around 8. You can also see a histogram distribution of the results. So, for example, we see that here, the most of the results are between 6 to 8. Here, an interesting diagram here is the mean reward score for overall episodes. So this reward score is basically calculated based on the reward function that you have defined, so your objectives. You see, policy or AI agent is always trying to maximize the reward function. So it has started from -8, and it's been able to improve it to around 5.5. So you see here 4 different curves. Each of these curves are fun trials. Each of these trials include a number of episodes or simulation runs that AI agent is running with different hyperparameters. So it starts with a random hyperparameter, but over time it refines it and finds the best one until it converges, until all the lines converge. And each trial here, when they, once in a while, they look at each other and see which set of hyperparameters are doing better. So they inherit those hyperparameters and build on top of that and try to improve that one. So this experiment is finished. You see the export policy button here. Let's export the policy. The policy is a zip file, so you can just export it and download it here. And let's go back to the model. Here, you can see in the Pathmind helper, there are two modes. One is use the policy and one is use random actions. Now that you have the policy, you can just browse to the file and choose the policy that you want. So when policy is selected, to see the results and validate that the policy is working well, you have to run Monte Carlo experiments. Monte Carlo simulations or experiments are a way of obtaining accurate estimate when working with uncertainties. And since this model has a lot of randomness in it, we have to run Monte Carlo experiments. So let's run it and see. We have created this Monte Carlo experiment and this UI for this experiment. So let's run with policy and see the results. All right. So the total profit, as we see here, is about 1,919,000. Okay. And total number of failures is 7. Work cost is 150K. Let's run it with the scheduled heuristic, which basically is visiting. Each service crew will visit equipments in a constant interval, like every month or every week. Okay, for this scenario, as we see, profit is much lower, 1,177K. Travel cost is about the same, but number of missions is much lower. That means that service crew have been running around for longer distances, but not being able to do as many missions as possible, meaning that they do not choose equipments efficiently. It chooses a equipment further away rather than choosing an equipment nearby. As you see, total number of failures is 137 here. All right, let's run with the predicted remaining useful life heuristic, which is service crew attend to equipments when their remaining useful life falls below a certain limit. So as you see, profit is not much better than scheduled, a bit better than scheduled. Travel costs about the same, number of missions still hasn't been efficient with how to choose the equipments, and total number of failures is 147, which is high. So as you see, Pathmind policy is able to increase the profit by about 65%. All right, that's it for this model. I will quickly walk you through another model, a very different model too, to show you the range of problems that RL can solve. This model is Bass diffusion, which is widely used in supply chain problems. It is developed by Frank Bass, and it's a tutorial model in any logic. You can build it step by step following any logic help. The objective for this model is to at the end of 1.5 years to have at least 80,000 adopters while minimizing the total expenditure. So for this, this simulation, now it was using Pathmind. You can see that Pathmind has made about $3,000 over 1 month. But if I run with Optimizer, now you see that the Optimizer, the strategy that it has followed is that it has made smaller expenditures, but over 3 months. So in total, it has expended $5,500 over 3 months, and it has reached the same number of adopters. So Pathmind policy is able to reduce the total expenditure in about half. So going back to the model, here is the Pathmind helper. Observations are very simple for this model. So how many potential adopters there are, how many adopters there are, and how much the simulation has progressed. So the duration is fixed, 1.5 years. Policy sees in which months we are. In the metrics, there are total expenditure, number of adopters, and if it has met the goal or not, which is 80,000 adopters. And do action, the action space for this policy is that it chooses to turn off the policy or not, and also it chooses to how much expend on advertising on each month. Yeah, simple as that. It learns to minimize the costs in about a half. Going to Pathmind web app, here is the experiment that policy has been trained in. You see that that the upward trend in the learning curve, it goes up, and it is number of adopters are constantly going higher, and total expenditure decreasing. All right. Well, thank you, everyone. That was it. Please make sure to check out our other presentation. One is presented by Johnny Davenport, is one of our reinforcement learning scientists. So the title is Harnessing Deep Reinforcement Learning to Coordinate Automated Guided Vehicles, or AGVs. And the presentation is on Monday, April 12th. The next exciting presentation is given by Luigi Manca, and it is about deep reinforcement training and machine learning applications for Industry 4.0. It's on April 13th. Well, thank you so much, and we will be ready to answer your questions in Q&A session.